In this video, we will learn how to deal with problems that involve the E2 mechanism and chair cyclohexane. Now, in this video, we will begin by reviewing some skills involving chair cyclohexane that you should already have learned when you were studying for your first midterm. And then later in this video, we will apply those skills to solve problems involving the E2 mechanism. Of course, if you feel that you're already familiar with these basic skills, you can just skip to the later part of the video that deals with applying those skills to the E2 mechanism. As usual, you can use the problems document as a kind of table of contents to the video that can help you to find the parts of the video that will be helpful to you. Now, you should have learned how to draw a chair conformation when you were studying for your first midterm, but let's review that skill together. So hopefully this will be a review problem for you. Please pause the video and try this problem. Let's start by numbering all the carbons. I've numbered the carbons, and now I'm going to draw the basic outline of chair cyclohexane. Here's a basic picture for chair cyclohexane. Let's transfer our numbers over. By the way, this picture is called the flat picture. This is a flat picture of cyclohexane showing a flat ring. This shows the ring in a chair. Notice that in our flat picture, the numbers are arranged counterclockwise. 1, 2, 3, 4, 5, 6 is arranged counterclockwise, so make sure that you get that matched up in your chair. 1, 2, 3, 4, 5, 6 arranged counterclockwise. Now I'm going to draw the bonds on, extra bonds on each of the atoms in the chair. Now I'm going to label each of these bonds as pointing up or down. Each U indicates a bond that's pointing up, and each lowercase d indicates a bond that's pointing down. Now I think it's obvious that this bond is pointing up. This bond isn't pointing straight down, but it is pointing partially down. Similarly, obviously this bond is pointing straight down. This bond is not pointing straight up, but it is pointing partially up. So that's how we distinguish between the up and the down positions for all the bonds on the ring, for all the substituents on the ring. Here's the rule that we can use to go from the flat picture to the chair picture. Substituents on wedges in the flat picture should be drawn up in the chair picture. Substituents on dashes in the flat picture should be drawn down in the chair picture. So, for example, on carbon 1, the chlorine in the flat picture is on a wedge. Therefore, in the chair picture, the chlorine should be drawn up. And the chlorine is on carbon 1. So here's where we draw the chlorine here. The chlorine goes from the wedge on carbon 1 in the flat picture to the up position on carbon 1 in the chair picture. So we should know that here there's a hydrogen in the down position. Let's try that for this substituent, carbon 7. Carbon 7 is on a dash connected to carbon 4. So a dash connected to carbon 4 in the flat picture should change into the down position in the chair picture, and that's on carbon 4. So here in the down position, I'm going to put carbon 7. Carbon 7 was on a dash connected to carbon 4 in the flat picture. Therefore, carbon 7 should be in the down position connected to carbon 4 in the chair picture. And in this up position, we should put a hydrogen. To match the hidden hydrogen from the flat picture. Okay, those are really the only substituents here. For completeness, we can draw in all the other hydrogens. So now we've completed this problem. In our chair picture, we've shown all the substituents, including all of the hydrogens, and we've labeled all those substituents as up or down. Well, I guess we've completed this part of the problem. And now you can see why these terms up and down are useful. The terms up and down are useful because of this rule. The terminology of up and down helps us to go from the flat picture to the chair picture. Substituents on wedges in the flat picture are drawn in the up position in the chair picture. Substituents on dashes in the flat picture are drawn down in the chair picture. Make sure you memorize this rule if you hadn't already been familiar with it. Now we can go ahead and do the next part of the problem and label all the substituents as axial or equatorial. Now I've labeled all the axial and equatorial substituents. You were probably already familiar with those terms from earlier in your course. Notice that the axial substituents are all pointing either straight up or straight down. Axial substituents point either straight up or straight down. Make sure that you really do draw all your axial substituents straight up or straight down. And notice that the equatorial substituents are all pointing either slanting down or slanting up. Slanting down or slanting up. Slanting down or slanting up. Make sure that you don't draw any of the equatorial substituents pointing straight down or straight up. Every carbon in the ring should have one substituent that's on a vertical bond and one substituent on a slanting bond. One substituent on a vertical bond, one substituent on a slanting bond. One substituent on a vertical bond, one substituent on a slanting bond. That's the correct way to draw the substituents for chair cyclohexane. Notice that axial and equatorial is not the same as up and down. Here we have an up axial, but here we have a down axial. Here we have an up equatorial, but here we have a down equatorial. And notice that when you're going from the flat picture to the chair picture, the rule is not based on axial or equatorial. The rule for going from the flat picture to the chair picture is based on the up-down terminology, not the axial-equatorial terminology. So now we've completed this problem. Now it should be obvious that there are many correct answers for this problem. Your chair picture might look different from mine and still be correct. There's many correct ways to draw the chair picture. This is just one of the possible correct chair ways. By the way, I should also say that this rule is not the only correct way to draw a chair picture. You don't have to follow this rule, but this is, I think, by far the simplest approach for a beginning student. This is the approach a beginning student should use. So how can you check if your chair picture is correct? Well, make sure that you've numbered both of your pictures. Make sure that you have the same clockwise or counterclockwise arrangement of the numbers in both your flat picture and your chair picture. Here the numbers are arranged counterclockwise, so here my numbers are arranged counterclockwise. Make sure that you follow this rule. All the wedges in the flat picture become up in the chair, and all the dashes in the flat become down in the chair. That's a good way to check whether your chair picture is correct. By the way, for most problems, it's not a good idea to show all the hydrogens on the chair picture. That just adds unnecessary clutter. For these problems that we're working on right now, we're showing the hydrogens to help build our understanding of the chair picture. But eventually you'll get to the point where it's not necessary or useful to show all the hydrogens on the chair picture. You want to keep most of the hydrogens out to avoid clutter. Okay, now let's try our next problem. The next problem asks you to do a chair flip. And again, this should really be a review of material you studied for the first midterm. So please pause the video and try this problem. Now we'll go through it. Here's the outline of the chair flip. So do you see why these are called chairs? Do you see why these are called chair pictures? So in this picture, carbon 4 would be the headrest. And then this portion here would be the seat of the chair, and carbon 1 would be the footrest. Can you see that chair? So you notice the seat here is drawn kind of at an angle. That the person who's sitting in this chair, I guess, would be reclining backwards a little bit. So this is like a chair, like an easy chair, I guess, that you're reclining backwards in. So can you see carbon 4 in this picture is the headrest. This portion right here is the seat of the chair. And carbon 1 would be the footrest. Now, when you do a chair flip, the number of the far right carbon stays the same in both pictures, and the number of the far left carbon stays the same in both pictures. carbon 1 is the far right carbon in this picture, so this far right carbon should also be carbon 1. Carbon 1 was on the far right in this picture, so carbon 1 is on the far right in this picture. Carbon 4 is on the far left in this picture, so carbon 4 is on the far left in this picture. Now we can add the other numbers. Remember to keep the same counterclockwise arrangement. The numbers here are arranged counterclockwise. 1, 2, 3, 4, 5, 6. So counterclockwise from here, we have 1, 2, 3, 4, 5, and 6. So again, the rule for the chair flip is that the number on the far right in this picture is the same number on the far right in this picture. And the number on the far left in this picture is the same number on the far left in this picture. This is not the only way to do a chair flip, but it's the best way for a beginner. Do you see how this chair flip again represents a reclining chair? In this case, we have a chair, a reclining chair where the chair is facing to the right, and here the chair is facing to the left. In this picture, carbons 2, 3, 5, and 6 represent the seat of the chair. And in this picture, again, the same carbons, 2, 3, 5, and 6, represent the seat of the chair. In this picture, carbon 4 was pointing upwards as the headrest. In the chair flip, we flipped carbon 4 to point down. Now in this picture, carbon 4 is representing the footrest of the chair. In this picture, carbon 1 was pointing down, representing the footrest of the chair. But in the chair flip, we flipped carbon 1 to an upwards position. So in this picture, carbon 1 represents the headrest of the chair. So in the chair flip, the headrest of the chair, so to speak, gets flipped downwards to become the footrest. And the footrest of the chair, so to speak, gets flipped upwards to become the headrest. So I hope you can visualize how this is a reclining chair where the chair is facing to the right, and this is a chair where the chair is facing to the left. Now we have to draw in the substituents, and here's the rule that will help us to get the correct orientations of the substituents. Here's the rule. The substituents that are up before the chair flip stay in the up position after the chair flip, and the substituents that were down before the chair flip stay down after the chair flip. So for example, on carbon 1, how should I draw the chlorine? Or I guess I'll start by drawing both of the bonds on carbon 1. So there should be an axial bond pointing straight up from carbon 1 and an equatorial bond pointing partially down from carbon 1. But where does the chlorine go here? Well, the chlorine was pointing up before the chair flip, so the chlorine should still be pointing up after the chair flip. This hydrogen on carbon 1 was down before the chair flip, so the hydrogen should still be down after the chair flip. So we followed this rule to figure out where to put the chlorine in this picture. We drew the chlorine in the up position after the chair flip because the chlorine was in the up position before the chair flip. Now we can do the same thing with carbon 7 in this picture. I guess I'll start by drawing the two bonds on carbon 4. Here's the two bonds on carbon 4. One bond pointing straight down and one bond pointing partially up. Now carbon 7 in this picture was pointing down. So carbon 7 should still be in the down position after the chair flip. The hydrogen on carbon 4 was pointing up before the chair flip, and therefore the hydrogen on carbon 4 should still be pointing up after the chair flip. Again, because carbon 7 was pointing down from carbon 4 before the chair flip, carbon 7 should still be pointing down from carbon 4 after the chair flip. That's how we can use this rule to draw the substituents in the correct position after the chair flip. To avoid clutter, I'm not going to bother drawing all the hydrogens on the other carbons now. I won't bother drawing all the other hydrogens, but we can complete the problem by labeling the substituents that we're showing as axial or equatorial. So remember, axial substituents point straight up like this chlorine or straight down like carbon 7. and the equatorial substituents point partially down, like this hydrogen, or partially up, like this hydrogen. Now, something that's very important to notice is that when you do a chair flip, the chair flip does not change the up-down orientations. Things that were up before the chair flip stay up after the chair flip. But did you notice that doing the chair flip does change the axial and equatorial arrangements? Notice that the chlorine was equatorial before the chair flip, and the chlorine changed to axial after the chair flip. Carbon-7 was equatorial before the chair flip, but carbon-7 changed to axial after the chair flip. That's one way in which the up-down terminology can sometimes be more useful than the axial-equatorial terminology. Up-down terminology can be more useful because the up-down orientations stay the same before and after a chair flip, whereas the axial and equatorial orientations change before and after a chair flip. Substituents that are equatorial before the chair flip become axial after the chair flip. Substituents that are axial before the chair flip become equatorial after the chair flip. By the way, let me just mention how useful I think numbering is on these problems. On this previous problem going from flat to chair picture, and on this problem going between the two chair flips, I think it's really crucial for a beginning student to be numbering all the carbons. That's almost always the case for any OChem problem. For almost any OChem problem, it's useful for a beginning student to number all the carbons. But of course, that only works if you're numbering the carbons consistently. It would be useless to number this picture unless I was trying to number consistently with the first picture. It's useless to number this picture unless I'm trying to number consistently with the flat picture. So of course, it would be useless to start using all new numbers in the chair picture. If I numbered these carbons 1 through 10, it would be useless to start using numbers 11 through 20 in the chair picture. Number all your pictures consistently. That's when the numbers are useful. So we've learned how to go from a flat picture to a chair picture using this rule. And we've learned how to go between two chair flips using this rule. Now, when you compare these two chair flips, which is the preferred chair flip? Which is more stable? The molecule can flip back and forth between these two conformations. Sometimes the molecule will look like this on the left, and sometimes it'll flip and look like this on the right. Well, here's the rule for choosing between the chair flips. You should have studied this rule for your first midterm. We prefer to put the larger substituent in an equatorial position. It is less preferred to put the larger substituent in an axial position. So in this case, the larger substituent is the tert-butyl group. This tert-butyl group is larger than this chlorine because this tert-butyl group is made up of a bunch of atoms. It's made up of 4 carbons and 9 hydrogens, whereas the chlorine is made up of only 1 atom. So the tert-butyl group takes up a lot more space than the chlorine. So we prefer the chair flip that puts this tert-butyl group in the equatorial position. Well, this is the preferred chair flip because it puts the tert-butyl group in the equatorial position. This is less preferred because here the tert-butyl group is in the axial position. So there's an equilibrium between these two chair flips. Sometimes the molecule will look like this chair flip, and sometimes it will look like this one. It changes back and forth between the two chair flips, but this flip is preferred. This flip is preferred. So notice that in this equilibrium arrow, I've shown that the equilibrium favors the reverse direction here. The equilibrium favors the flip on the left and disfavors the flip on the right. This is the way to show an equilibrium where the left-hand picture is favored and the right-hand picture is less favored. The molecule will spend the majority of its time in this chair flip and a minority of its time in this chair flip. Why? Why is it better to put the larger substituent in the equatorial position? Because the larger substituent will experience less steric hindrance in the equatorial position. There's less steric hindrance from the other substituents when the large substituent is in the equatorial position rather than the axial. That's actually probably not obvious from these pictures. From these pictures, it's probably not obvious that the equatorial position has less steric hindrance. I'm not going to go further and try to demonstrate that. We'll just memorize that the equatorial position has less steric hindrance and is preferred for the larger substituent. Now we can go further in this case because this tert-butyl group is not just a large substituent, we could consider it a very large substituent. Again, remember this tert-butyl group actually consists of 4 carbons and 9 hydrogens. So it actually would take up quite a bit of space. Because this is a very large substituent, the equatorial position is not just preferred, it's strongly preferred. So in fact, I should draw the equilibrium like so. We can draw the equilibrium like so to show that, in fact, with this very large substituent, the molecule will spend almost all of its time in this preferred chair flip and almost none of its time in this less preferred. So just to make up some numbers, maybe the molecule will be spending, I don't know, 99.9% of its time in this chair flip and only 0.1% of its time in this less preferred chair flip. Those are just made up numbers, but they illustrate the idea that we'll be spending almost, with this very large substituent that strongly prefers the equatorial position, the molecule will spend almost all of its time in the preferred chair flip and almost none of its time in this less preferred picture. We can say that a very large substituent, like a tert-butyl group, almost locks the molecule in one of the chair flips. This molecule is virtually locked in this chair flip. It's very difficult for it to change to the less preferred chair flip. So the tert-butyl group is pretty important because it's the most typical example of a very large substituent. Do you see why this is called a tert-butyl group? Obviously, it's not tert-butyl oxide because it's not connected to an oxygen. Here is the tert-butyl group. Where does this name come from? Well, it's called tert because carbon 7 here is attached to 3 other carbons inside the substituent. So we could say that carbon 7 is tertiary relative to the substituent. Notice that for this naming, we're disregarding carbon 4. If we disregard carbon 4 because it's outside of the substituent, we could say that inside the substituent, carbon 7 is attached to 3 other carbons. So relative to the rest of the substituent, carbon 7 is tertiary. And it's called butyl because remember that but is the root for 4 carbons. Butane means 4 carbons, and there are 4 carbons total inside this substituent. So that's why this important type of substituent is called a tert-butyl group. You need to be able to recognize a tert-butyl group. In the past, we've talked a lot about tert-butyl oxide. Well, you can see that tert-butyl oxide is called that because it contains a tert-butyl group. Tert-butyl oxide contains a tert-butyl group as well as the O-, which is what the oxide is referring to. Tert-butyl oxide contains a tert-butyl group connected to O-. This molecule contains a tert-butyl group that is not connected to O-, that's just connected to the ring. So this is not tert-butyl oxide, but it does contain a tert-butyl group. To summarize, large substituents prefer to be in the equatorial position. Very large substituents, such as a tert-butyl group, strongly prefer to be in the equatorial position. Now remember that we learned in an earlier video a requirement for E2. In order for E2 to occur, the leaving group and the beta hydrogen must be oriented in an anti-periplanar conformation. This is a mandatory requirement for E2. Now, how would we apply this requirement to cyclohexane? Here's how this requirement applies to cyclohexane. For a cyclohexane ring, in order for the leaving group and beta hydrogen to be tied to each other, they must both be in axial positions in a chair conformation. And let's illustrate that here below. So notice here we have a chlorine that is in an axial position. And what about the beta hydrogens? Our beta carbons here are carbons 2 and 6. I drew in the beta hydrogens on the beta carbons 2 and 6. Now, do you see how this chlorine, this axial chlorine, could do an E2 with this axial hydrogen? This hydrogen is axial, this chlorine is also axial, and I think you can see they really are oriented anti to each other. The chlorine is pointing straight up from the ring, and the hydrogen is pointing straight down from the ring. So they really are pointing in exactly opposite directions. They really are oriented anti to each other. So you can see that in order to get an anti-conformation between the leaving group and the beta hydrogen, they really do have to be in the axial positions on the chair conformation. Notice that this chlorine could not do an E2 with this hydrogen. Notice this hydrogen is in the equatorial position, which means it can't do an E2. And I think you can see that this bond is not anti to this bond. I think it's pretty obvious that this hydrogen is not pointing in the opposite direction as this chlorine. This chlorine is pointing straight up, and this hydrogen is pointing partially up. So clearly they're not pointing anti to each other. So that should help you to give you a better intuition for why both the leaving group and the beta hydrogen have to be in axial positions in order for them to be anti to each other. You could also say to yourself that this chlorine and this hydrogen are cis to each other. They're cis, they're both pointing up from the ring, but we've already learned that for E2 you have to use a leaving group that's trans to the beta hydrogen. This chlorine and this hydrogen are trans to each other because one's pointing up and one's pointing down. So similarly, we could use this hydrogen for E2. Notice that this hydrogen on the other beta carbon is also in the axial position. So this axial hydrogen would also be anti to this axial chlorine and could be used for E2. And this hydrogen could not be used for E2. It's in an equatorial position. Again, the chlorine is pointing straight up, and this equatorial hydrogen is pointing partially up. So they're not anti to each other. Again, that illustrates that you need to use an axial hydrogen and an axial leaving group for E2. Neither can be equatorial. So we've seen that E2 is possible in this chair flip because the leaving group is axial and there are beta hydrogens that are also axial. What about in this picture? Well, notice that in this picture, the leaving group is equatorial. But we know that when the leaving group is equatorial, E2 is impossible. E2 is impossible in this chair flip because the leaving group is equatorial. But E2 can't occur when the leaving group is equatorial. Can you see why? Draw in the beta hydrogens. Again, the beta carbons would be carbons 2 and 6, so I drew in their beta hydrogens. Can you see that this chlorine is not anti to any of those beta hydrogens? For example, this chlorine is on a bond that's pointing up and right. This bond is pointing up and right. Well, this bond is pointing straight up. That's not anti to up and right. This bond is pointing down, which is opposite to up, but it's pointing down and right. Down and right is not completely opposite to up and right. Down and right is not completely opposite to up and right. And if you wanted them to be completely opposite, you'd need one to be up and right and one to be down and left. And that's not what we're getting here. The opposite, anti to up and right, would be down and left. But we don't see anything like that here on the beta carbons. None of the hydrogens are in that position. The thing that's pointing down and left from carbon 2 is a carbon, not a hydrogen. This is the thing that would be anti to this chlorine. This chlorine is anti to carbon 3. because the chlorine is pointing up and right, and carbon 3 is if you go on the bond from 2 to 3, that's pointing down and left. So this chlorine is anti to carbon 3, but that's no good. We need the chlorine to be anti to a hydrogen, not to a carbon. So we're just trying to illustrate that E2, it really is impossible for the chlorine to be anti to a beta hydrogen when the chlorine is in an equatorial position. And you could say the same thing about these hydrogens. Neither of these two hydrogens is exactly anti to this chlorine. Again, the chlorine is pointing up and right. That's clearly not anti to this hydrogen, which is pointing straight up. And this hydrogen is pointing down and right. Well, down and right is not 100% anti to up and right. So again, this chlorine is not anti to that hydrogen. I hope this is making sense to you. But you could also just memorize that E2 requires both the leaving group and the beta hydrogen to be in axial positions. E2 can't occur if either the leaving group or beta hydrogen is equatorial. I tried to illustrate why that is, but also you can just memorize that fact. So we've decided that E2 is impossible in this chair flip because the leaving group is in the equatorial position. E2 is possible in this chair flip because the leaving group is in an axial position, and there are also beta hydrogens that are in the axial position. So do you think that E2 would be fast or slow for this molecule? Remember that both of these pictures are of the same molecule. This molecule is the same as this molecule. These are different conformations of the same molecule. Will E2 be fast or slow for this molecule? Pause the video and come up with an answer. Well, the answer was that E2 would be very slow for this molecule. So the way to figure that out is remember that the molecule is going to spend almost all of its time in this chair flip on the left, not in the chair flip on the right. Here's our answer. E2 will be very slow for this molecule, and I hope you gave an explanation. We know that the molecule is going to spend almost all of its time in chair flip A and almost none of its time in chair flip B because chair flip A puts the large tert-butyl group in the favored equatorial position. But remember that E2 is actually impossible in this chair flip. E2 is only possible in chair flip B because chair flip B is the one that puts the leaving group in an axial position, which is the only time that it can be anti to a beta hydrogen. Therefore, E2 will be very slow for this molecule. Notice that all these ideas are already kind of coded in for how I've drawn this up here. I've already mentioned that E2 is impossible in this chair flip and that E2 is possible in this chair flip. I've shown how the leaving group and the beta hydrogens are axial here, and I've shown that chair flip A is strongly favored with how I've drawn the equilibrium arrow. Notice that I've shown the equilibrium arrow strongly favoring A and strongly disfavoring B by making the arrow to the left much, much longer than the arrow to the right. So the way I've drawn this actually codes in all the information that I wrote down here in this written explanation. For illustration, we might say that the molecule is going to spend maybe 99% of its time in chair flip A and maybe only 1% of its time in chair flip B. Those are just made up illustrative numbers. But that means that 99% of the time, E2 will be impossible. And only during this rare 1% of the time will it even be possible for E2 to occur. So E2, if a base happens to bump into the molecule during the 99% of the time when it's in chair flip A, no E2 can occur. E2 can only occur if the base happens to bump into the molecule during this very rare 1% of the time when it's in chair flip B. And as a result, E2 would proceed very slowly, very, very slowly for this molecule. Remember, these are not two different molecules. These are two different conformations of the same molecule. These are two different pictures of the same molecule. This molecule spends the vast majority of its time in this conformation and a small minority of its time in this conformation. So we can adapt what we've been talking about into a new guideline for an E2 mechanism. Here's a new guideline when you're doing an E2 mechanism on a ring. Now notice that this guideline applies when you're dealing with a cyclohexane ring. Do you know what cyclohexane is? Cyclohexane means a ring with 6 carbons. Hex means 6 carbons. So a cyclohexane ring contains 6 carbons. So when you have a 6-carbon ring with a large substituent, that's when you often need to draw the chair conformation. If you see a 6-carbon ring with a large substituent, such as usually a tert-butyl group, you need to draw the chair conformation to help you with the E2 mechanism. Now remember, there's actually 2 different chair conformations. The more stable chair conformation will put the large substituent in the equatorial position. And you need to know that the leaving group and the beta hydrogen have to both be in axial positions in order for E2 to occur. So we applied these guidelines in this example that we've been talking about. Notice that here we have a 6-carbon ring, a ring with 6 carbons. So this is a cyclohexane ring, and it does have a large substituent. It has a tert-butyl group, so we drew the chair conformation. We figured out that the more stable chair conformation was A, because that put the large group in the equatorial position. But we also figured out that E2 was only possible in chair flip B, because that was the chair flip where the leaving group and the beta hydrogen were both in axial positions. So we determined that E2 would proceed very slowly for this molecule, because E2 can only occur during the rare times that the molecule is in the less favored B chair flip. So be careful when you're learning these rules. Notice that you can't just learn equatorial good or axial good. You can't just say in your mind equatorial good or axial good. You need to be more detailed. Remember that the equatorial position is the better place to put the large substituent. The equatorial position is the better place to put the large substituent to give you the more stable chair conformation. But on the other hand, the axial position is the only place where we can put the leaving group and the beta hydrogen and still get an E2. So we need the leaving group and the beta hydrogen to be axial in order to accomplish E2. So these ideas are more complicated than equatorial good or axial good. So try to learn these ideas in more detail so that you can see what the role of equatorial and axial is in this thought process. Equatorial is good, so to speak, if you're trying to figure out the more preferred chair flip for the large substituent. But axial is good, so to speak, if you're trying to figure out the right positions that the leaving group and the beta hydrogen have to be in order for E2 to occur. So rather than saying that equatorial is good or axial is good, you have to memorize the actual ideas. The more stable chair conformation puts the large substituent in the equatorial position. And E2 is possible only when the leaving group and the beta hydrogen are both in axial positions. If E2 is only possible for the less stable chair flip, that means that the E2 reaction will proceed very slowly. If E2 is possible for the more stable chair flip, that means that the E2 reaction will proceed more quickly. I've updated the guideline here a little bit to be a little bit more specific. Decide which chair flip is more stable. That's the one that puts the large substituent in the equatorial position. Determine which chair flip makes E2 possible. That's the one where the leaving group is axial. If E2 is possible only for the less stable chair flip, then E2 will proceed slowly. That was the case with this molecule. E2 is possible only for chair flip B, which is the less stable chair flip, so E2 proceeds very slowly for this molecule. On the other hand, if you had a different molecule where E2 was possible for the more stable chair flip, then E2 would proceed relatively quickly. Please pause the video and try this problem. Now let's discuss. Well, in this case, we want to focus especially on this guideline. We have cyclohexane rings, rings with 6 carbons, which bear a large substituent. Both of these rings bear a tert-butyl large substituent. That means that this, the key to this solution is probably going to be based on drawing the chair conformation. So we need to start by drawing chair conformations for these molecules. Well, did you recognize that molecule X was the molecule that we already had analyzed earlier in this video? So we can just repeat the analysis we already made for molecule X earlier. So first of all, we have to translate molecule X into a chair flip. And we would do that like this. I should number all the carbons again. Remember, since the numbers 1, 2, 3, 4, 5, 6 are arranged counterclockwise in this pictures, the numbers 1, 2, 3, 4, 5, 6 are also arranged counterclockwise in these two pictures. Since this chlorine is on a wedge in the flat picture, it changes to up in the chair picture. And since carbon 7 is on a dash in the flat picture, it changes to down in the chair picture. So this is one of the chair flips, and this is the other chair flip. Remember that when we move between the chair flips, the carbons on the far right and the far left stay the same. In this chair flip, carbon 1 is on the far right and carbon 4 is on the far left. So in this picture, carbon 1 is on the far right and carbon 4 is on the far left. And remember that since the chlorine is up in this chair flip, the chlorine stays up in this chair flip. Carbon 7 points down in this chair flip, so carbon 7 remains pointing down in this chair flip. And remember, our analysis was that this chair flip was favored and this was disfavored. This was the favored chair flip because it put the large tert-butyl group in the equatorial position. This was a disfavored chair flip because it put the large tert-butyl group in the axial position. I showed that with the equilibrium arrows, showing that the chair flip on the left is far more favored than the chair flip on the right. That's why this leftward arrow is far larger than the rightward arrow. But on the other hand, E2 is impossible in this chair flip because in this chair flip, our leaving group is equatorial. E2 is only possible in this chair flip because in this chair flip, the leaving group is axial. For E2 to work, the leaving group must be axial. It's a good idea for this type of problem to actually draw the E2 mechanism. Let's go ahead and draw the E2 mechanism. This problem hasn't actually told us who the base is for this E2 mechanism, so I'll just invent a generic base, capital B, to use in the E2 mechanism. And we did an arrow for the base taking the beta hydrogen, an arrow for the pi bond forming between alpha and beta carbons, and an arrow for the leaving group leaving the alpha carbon. I will not draw the E2 mechanism in this chair flip because remember E2 is impossible in this chair flip. All right, and remember we saw that E2 would be very slow for molecule X because the E2 can only occur in the disfavored chair flip. Here's the reasoning we already went through earlier in this video. For molecule X, this flip is favored over flip B because it puts the large tert-butyl group in the equatorial position. But E2 is not possible in this favored chair flip. It's only possible in this disfavored chair flip because this is the one that puts the chlorine leaving group axial to the beta hydrogen. So if that's what these arrows are showing, so if, for example, we might say that maybe the molecule will spend only 1% of its time in chair flip B, and only during that 1% of the time will E2 be possible. Therefore, E2 proceeds very slowly for molecule X. Now we're not done yet, because for completeness, for full credit, we have to also explain why E2 is fast for molecule Y. So now we have to go through this whole analysis all over again to explain why E2 is relatively fast for molecule Y. If you haven't done that already, you should try that on paper. Now let's go through that together. Well, remember, according to our guideline, we need to draw the chair picture for molecule Y. We'll start by numbering all the carbons. Remember that molecules X and Y are two different molecules. These are different molecules because there's no free rotation around a ring. There's no easy way to rotate carbon 7 In this picture, carbon 7 is trans to the chlorine, and in this picture, carbon 7 is cis to the chlorine. And because there's no free rotation around a ring, you can't just rotate carbon 7 from trans to cis. If carbon 7 starts trans, it's stuck in that position. So these are two separate molecules. Normally, I would not I would give different numbers to different molecules, but because these two molecules are so similar, and because our whole goal is to compare them, I'll give similar numbers to the two molecules. Now let's try drawing the chair picture for molecule Y. Here's an outline of a chair. Remember that numbers 1, 2, 3, 4, 5, and 6 are arranged counterclockwise in this picture. So for consistency, I arranged 1, 2, 3, 4, 5, and 6 counterclockwise in this picture. Let's apply this rule. The chlorine is on a wedge in this picture, so the chlorine should be pointing up in this picture. Carbon 7 is on a wedge in this picture, so carbon 7 should be pointing up in this picture. We used this rule to go from the flat picture to the chair picture. Since these substituents were both on wedges in this picture, they both ended up pointing up in the chair picture. Of course, this chlorine isn't pointing straight up, but it's pointing partially up, which counts as an up position. Now let's do the chair flip. Here's the outline of the chair flip for this molecule. Notice that in this picture, carbon 4 is pointing up as the headrest, and in this picture, it's flipped down to be the footrest. In this picture, carbon 1 is pointing down as the footrest, and here it's been flipped up to be the headrest. Now we have to move the substituents over. The chlorine was up in this chair flip, and therefore the chlorine should stay up in this chair flip. Here the chlorine is still pointing up in this chair flip. It went from partially up to straight up. And in this picture, the carbon 7 was pointing up, so it should stay pointing up in this picture. Carbon 7 pointed up in this picture, so carbon 7 is still in the up position after the chair flip. It went from straight up to partially up. So here's the rule that we've learned for going from one chair flip to the other chair flip. Substituents that start up in one chair flip remain up in the other chair flip. We can label the equatorial and axial substituents. The substituents on vertical bonds are axial. So here's an axial substituent and here's an axial substituent. And the substituents on the slanted bonds are equatorial. So here's an equatorial substituent and here's our other equatorial substituent. Notice that when we do a chair flip, axial changes to equatorial and equatorial changes to axial. Using this guideline, the more stable chair conformation is the one that puts the large substituent in the equatorial position. So this is an unstable chair flip because here the large tert butyl group is axial. And this is a more stable chair flip because here the large tert butyl group is equatorial. Remember that this large group will face less steric hindrance when it's in the equatorial position. So I've drawn that with these equilibrium arrows. The arrow to the right is much longer than the arrow to the left, showing that the molecule is going to spend the great majority of its time in flip B and only a small minority of its time in flip A. Now, which of these chair flips can do an E2 reaction? Remember that E2 is only possible when the leaving group is axial. So E2 is impossible in this chair flip where the leaving group is equatorial. E2 is not possible in this chair flip where the leaving group is equatorial. E2 is possible in this chair flip where the leaving group is axial. Because remember, only when the leaving group is axial can it be anti to the beta hydrogen. The best thing is to actually draw the E2 mechanism to show that it's possible here. Which beta hydrogen should we use? This one or this one? Well, remember, also, in order to be anti, obviously the beta hydrogen has to be trans to the leaving group. So obviously this hydrogen is not anti to the leaving group. It can't be because it's cis. They're both pointing up. So we're not going to use that beta hydrogen. We're going to use this axial beta hydrogen that's trans to the leaving group. And you can see they definitely are anti, pointing in opposite directions. Here's the mechanism. showing that E2 mechanism when the leaving group is anti to the beta hydrogen. So this is the chair flip where E2 is possible, and this is also the favored chair flip. Remember, the molecule will spend the vast majority of its time in this chair flip, and this is where E2 is possible. Well, when E2 is possible for the more stable chair flip, that's when E2 will proceed relatively quickly. So now we've confirmed that E2 will proceed relatively quickly for molecule Y. For molecule Y, flip B is favored over flip A because this flip puts the large tert-butyl group in the equatorial position. And flip B is also the chair flip where E2 is actually possible because it puts the chlorine in an axial position, which allows it to be anti to the beta hydrogen. So E2 proceeds pretty quickly for molecule Y. And now we've decided, therefore, that E2 is much faster for molecule Y than for molecule X. Remember that because this picture is favored, just to make up some numbers for illustrative purposes, we might say that the molecule is going to spend 99% of its time in this picture, and maybe only 1% of its time in this picture. So it's almost always going to be in this chair flip, and during that 99% of the time that it's in this chair flip, it will also be possible for the molecule to do an E2 reaction. The only times it will be impossible for the molecule to do the E2 reaction are the rare 1% of the time, say, when it's in this less stable chair flip. So E2 is definitely going to be a relatively quick reaction for molecule Y. Drawing the equilibrium arrows in this way are trying to show that the molecule will spend much more time in the right-hand picture and much less time in the left-hand picture. All right, here's our complete explanation and answer. I probably written down more here than you would need to write down for full credit. I wrote down a very complete explanation for our own understanding. You probably wouldn't need to put in quite this much detail for full credit. But what you would need for full credit is you definitely would need to draw the chair picture for molecule X and the chair picture for molecule Y. It's not a bad idea to show both chair flips to show which is more stable and which is less stable. And you should also show which chair flip allows E2 and which one doesn't. And I think in many cases the professor is going to be looking for you to actually draw in the mechanism to show how E2 works for the chair flip where the leaving group is axial. You probably wouldn't need quite as much written explanation for full credit because a lot of what I wrote down here kind of repeats the ideas in this first written explanation. I think it is a good idea to use these types of equilibrium arrows to show which is the favored and disfavored chair flip. We used this guideline for dealing with a cyclohexane ring with a large substituent. We also really used this idea that the beta hydrogen has to be trans to the leaving group. That's how we knew we should use this hydrogen and not the equatorial hydrogen. Not the equatorial hydrogen has to be trans to the leaving group because that's the only way it can be anti to the leaving group. And remember when I drew this mechanism, here I used the beta hydrogen on carbon 6. You could just as well have used the beta hydrogen on carbon 2. There's also an axial beta hydrogen on carbon 2 here that you could have used to show the mechanism. So we've illustrated how to use these guidelines for a cyclohexane ring that bears a large substituent such as tert-butyl. Another comment about this problem, notice that the key to this problem was drawing the chair conformations. But notice that the problem never mentioned chair cyclohexane. There was no explicit clue in the problem that you needed to draw the chair conformation. So you need to be on the watch for situations where you need to draw the chair conformation. Remember, what's the clue for when you need the chair to draw the chair picture? When you're dealing with an E2 reaction on a cyclohexane ring with a large substituent, especially a tert-butyl group. When you see a cyclohexane ring with a large substituent like tert-butyl, there's a good chance that you might need a chair picture. Other than that, you just have to use your judgment and study the problem to see whether the logic that we went through about chair conformations is relevant for the problem that you're looking at. Obviously, most E2 reactions on a ring do not require a chair picture. Think about all the E2 reactions that we did in the previous video. In all the reactions in the previous video, those were all on rings, but none of them required us to draw the chair picture. So it's actually somewhat rare that you actually have to draw the chair picture. For example, here we had cyclohexane. Here we had cyclohexane, but it was possible to figure out an answer here without actually drawing the chair picture. You could draw the chair picture. If you wanted to, you could draw the chair picture and then draw the mechanism. In fact, in some ways, that might be a good exercise, but it might also take up unnecessary time during the exam. So if you want to draw the chair picture, you always can, but it's not necessary on the problems that we saw in the previous video. Please pause the video and try this problem. I hope that you really did try this problem on paper. This is a good test of whether you've understood the material so far in this video. Now let's go through this. We can start by numbering the carbons. We can notice this ionic bond and draw in the formal charges for that ionic bond between the metal potassium and the non-metal oxygen. Now, did you understand what this TBU stood for? I hope that you figured out that this is an abbreviation for a tert butyl group. This is an abbreviation you might see on your exams for tert butyl. So this is a tert butyl group. And here's another tert butyl group. So this is tert butyl oxide. This compound is tert butyl oxide, and this compound is tert butyl alcohol. So if you see this abbreviation on your exam, you should recognize that as representing a tert butyl group. Now we have to choose a mechanism. We expect to use the O- as a nucleophile or a base. The neutral bromine can be a leaving group, or this neutral bromine can be a leaving group. We don't know yet which of those will give us the major product, so we don't know yet whether we're going to use carbon 3 as our alpha carbon or carbon 5, but notice that either way we're going to have a secondary alpha carbon. Carbon 3 is secondary, and carbon 5 is also secondary. So either way we're going to have a secondary alpha carbon, which puts us in the middle row of the table. We're using O-, which puts us in the right-hand column of the table. So our table predicts an E2 mechanism. So we should write down that we're using an E2 mechanism. Don't assume the mechanism is E2. Use the table to determine the mechanism. Now remember, we just discussed that most E2 problems with cyclohexane do not require you to draw a chair picture. But this is a problem where we do need to draw a chair picture. What are the clues that we need a chair picture here? Well, a big clue is this tert butyl group. Remember, you especially are likely to need the chair conformation when the cyclohexane ring bears a large substituent, such as a tert butyl group. And the other clue that we need the chair picture is just that this is a fairly complicated and subtle problem with two different leaving groups. And since we need to draw the major product, we're going to have to find some way to decide which of these two leaving groups will give us the major product. So also the fact that this is just a more complicated and subtle E2 problem than normal is another clue that likely we'll be able to figure this out by drawing the chair conformation. Here's a chair picture. I'll put in some numbers. Notice that I happened to arrange the numbers in the flat picture clockwise, 1, 2, 3, 4, 5, 6 clockwise. So I have to be careful to arrange 1, 2, 3, 4, 5, 6 clockwise in the chair picture as well. Now we place substituents in the chair picture using this rule. So let's see, on carbon 2, carbon 7 is on a wedge, so carbon 7 should point up in the chair picture. A wedge in the flat picture becomes an up position in the chair picture. Then on carbon 3, the bromine was on a wedge, so the bromine should be pointing up in this picture. Wedge in the flat picture becomes up in the chair picture. On carbon 5, the bromine is on a dash, so this bromine should be pointing down in the chair picture. A dash in the flat picture becomes down in the chair picture. And this tert butyl group on carbon 6 was on a wedge, so that should be pointing up in the chair picture. The wedge in the flat picture becomes up in the chair picture. So we used this rule to go from flat to chair picture. As usual, numbering all your pictures consistently is key for getting the pictures right. Now let's do the chair flip and draw the other chair conformation. Here's the other chair conformation. Let's put in some numbers. Remember that the carbon on the far right, the number on the far right in this picture should also be on the far right in this picture, carbon 3. And the carbon on the far left in this picture, carbon 6, should also be on the far left in this picture, carbon 6. And then maintain the same clockwise arrangement of the numbers. 1, 2, 3, 4, 5, 6 is still arranged clockwise, with 3 on the far right and 6 on the far left, just as in this picture. Now we have to put in the substituents. We use this rule for the substituents. So carbon 7 was up in this picture, so carbon 7 should still be up in this picture. In this picture it was pointing straight up, and in this picture it's changed to slanting up. In this picture the bromine was pointing up, so the bromine is still up in this picture. The bromine changes from slanting up to straight up. In this picture the bromine points down, so in this picture the bromine should point down. The bromine changes from straight down to slanting down. And in this picture the tert butyl was pointing up, so the tert butyl should still point up in this picture. We used this rule. All the substituents that were up before the chair flip stayed up after the chair flip. All the substituents that pointed down before the chair flip stayed down after the chair flip. Students oftentimes have difficulty drawing this equatorial bond and this equatorial bond at the correct angle. So at the end of the explanation for this problem, I will include an additional note that explains how to draw this equatorial bond and this equatorial bond at the correct angle. Which of these two chair flips is favored? Well, remember the more stable chair puts the large substituent in the equatorial position. So this is less favored because the large tert butyl is axial. This is more favored because the large tert butyl is equatorial. And because a tert butyl group is a very large group, there's a large difference in stability. So I drew this rightward arrow much longer than the leftward arrow to show we're going to spend almost all our time in the more stable chair flip and very little time in the less stable chair flip. This chair flip is better because the large tert butyl group will experience less steric hindrance in an equatorial position. Now we have to decide in which chair flip E2 is possible. E2 is only possible when the leaving group is axial. Well, here we have two possible leaving groups, two bromines which are possible leaving groups. So notice that in this picture, this bromine is axial, so E2 would be possible for this bromine in this chair flip. But that doesn't matter very much because remember, we want the major product. We want the major product. The major product will, since we're going to spend very little time in this chair flip won't give us the major product. Instead, we're going to be using this chair flip, and in this chair flip, it's this bromine that is axial. So in this chair flip, this bromine can carry out an E2, and this one cannot because it's in an equatorial position. In this chair flip, E2 is possible for this bromine because this bromine is in an axial position. And E2 is impossible for this bromine because this bromine is in an equatorial position. So now we can continue to try to draw the mechanism for the major product. Again, the major product will use this chair flip, not this chair flip, because this is the preferred chair flip. That puts the tert butyl group in the equatorial position. We're going to spend maybe 99% of our time in this chair flip and maybe only 1% in this chair flip. So this chair flip will give us the major product. So we can say that this will be our alpha carbon. Here we have a beta carbon, and here we have another beta carbon. There's two beta carbons, so we have to decide which one we're going to use. Well, carbon 2 has a hydrogen in an axial position. Carbon 2 has a beta hydrogen in an axial position, trans to the leaving group, and carbon 4 also has a beta hydrogen in an axial position, trans to the leaving group. So we could use either of these two hydrogens. Which one will give us the major product? Well, now we have to use this guideline for the major product, comparing which is the more and which is the less substituted beta carbon. Well, this beta carbon is secondary. Beta carbon 4 is attached to two carbon chains, carbon 3 and carbon 5, so this beta carbon is secondary. This beta carbon is tertiary because it's attached to carbon 1, carbon 3, and carbon 7. Now remember that the base for this problem is tert butyl oxide. The problem told us that we were using tert butyl oxide. And remember that tert butyl oxide is an exception. When using tert butyl oxide, the major product for E2 uses the less substituted beta carbon. This tert butyl oxide will prefer to attack the less substituted beta carbon because it has less steric hindrance, and tert butyl groups already create a lot of steric hindrance. So with this tert butyl group, we're going to apply this exception, and our major product will come from using the less substituted beta carbon. Draw that mechanism. So it took us a lot of work to figure out the mechanism for the major product. Let's go through the three main things we had to figure out. We had to realize that we're going to use chair flip B and not chair flip A for the major product. Chair flip B is more stable because it puts the large tert butyl group in the equatorial position. We also had to figure out that we were going to use this bromine as the leaving group and not this bromine, because in chair flip B, this bromine is in the axial position, and that's a requirement for E2. E2 is possible only when the leaving group is axial, because that's the only way that the leaving group can be anti to the beta hydrogen. And thirdly, we had to decide whether we were going to use carbon 2 or carbon 4 as our beta carbon. Well, we realized that we were using tert butyl oxide, and for tert butyl oxide, the major E2 product comes from using the less substituted beta carbon. That's how we decided to use carbon 4 and not carbon 2. And finally, notice that we didn't use this hydrogen. We didn't use this hydrogen because this hydrogen is not trans to the leaving group. Remember that you need to use, on a ring, you need to use a hydrogen that's trans to the leaving group. Like this one, that's the only way that they can actually be anti to each other. Now we can draw the product from that mechanism. This arrow tells us to draw a bond between this oxygen and this hydrogen. So here I've shown the oxygen covalently bonded to the hydrogen. The oxygen started negative and lost electrons, so the oxygen becomes neutral. This arrow tells us to break the bond between carbon 4 and the hydrogen. So we break off that hydrogen, and to form a pi bond between carbon 4 and carbon 3. So here's that new pi bond between carbon 4 and carbon 3, and this arrow tells us to break the bond between carbon 3 and the bromine. The bromine started neutral and gained electrons, so the bromine becomes negative. Here's the product that the professor would probably care about. So here's our major product. If you wanted to, you could now convert this picture back into a flat picture. You could convert this back into a flat picture, but that shouldn't be necessary. I think this would be a full credit answer. All right, so here's our answer to the problem. We drew the major product and the mechanism that led to it. This is a good review problem because it involves a lot of the ideas we've talked about previously. It talks about the ideas we've talked about for chair cyclohexane, but it also uses these ideas about choosing between a more substituted and a less substituted beta carbon. Notice again that this problem never mentioned chair cyclohexane. And remember that for most cyclohexane problems with E2, you don't need to draw the chair. But the clue here that we should draw the chair was, first of all, there was a large tert butyl group, and the other clue was simply that this problem was complicated enough that there was a good chance that the chair pictures would help us to resolve the complication. In particular, you can see we needed the chair pictures to decide which bromine to use. There's two bromines. How do we decide which one to use? Well, we decided by using the chair pictures. This bromine is axial only in the less favored chair picture that the molecule would be in only maybe 1% of the time. The molecule spends only about 1% of its time in this chair flip, so it would be pretty unusual for this bromine to participate in an E2 reaction. On the other hand, this bromine is axial in the chair flip that the molecule spends maybe 99% of its time in. So this is the bromine that's going to give us the major product for E2. So we really did need the chair pictures in order to figure out which bromine would give us the major product. Remember, it was crucial to realize we were using tert butyl oxide as our base. When you use tert butyl oxide, you prefer the less substituted beta carbon. On the other hand, without tert-butyl oxide, we would have preferred to use the more substituted beta carbon. So keep your eyes out for tert-butyl oxide. By the way, I think many students might have difficulty drawing this equatorial bond and this equatorial bond at the correct angle. So here's the right way to think about that. An equatorial bond should be parallel to a ring bond that is 2 positions distant from the equatorial bond. Here's what that means here. This equatorial bond, which I've labeled A, is 2 positions distant from this ring bond. So I've also labeled this as A. And again, this equatorial bond is 2 positions distant from this ring bond. So I've also labeled that as A. So that means that this equatorial bond should be parallel to the ring bonds that I labeled as A. This equatorial bond should be parallel to this bond and also parallel to this bond. You don't have to get that perfectly correct. I'm sure I didn't get it perfectly correct, but I tried to draw this bond approximately parallel to this bond and to this bond. Of course, that means this bond should be approximately parallel to this one if you draw the chair correctly. And we could use the same logic for this equatorial bond. This equatorial bond is 2 positions distant from this bond. So again, I've labeled this as A. And this equatorial bond is 2 positions distant from this equatorial bond. And again, I tried to draw this bond at roughly the same angle as all the other bonds that are labeled as A. That's the way to get the correct angle for these equatorial bonds. And of course, you could apply this rule as well to this equatorial bond. This equatorial bond, which I've labeled as B, is 2 positions distant from this equatorial bond. So I also labeled this bond as B, and this equatorial bond is 2 positions distant from this equatorial bond, which I also labeled as B. So again, all those bonds labeled as B should be parallel to each other. This bond should be parallel to this one, and they should both be parallel to this equatorial bond. And again, I tried to draw them all approximately parallel to each other. For completeness, we can mention that there's a third set of bonds here that we could label as C. Here's a C bond, and here's a C bond. So you would try to draw this C bond as approximately parallel to this C bond and this C bond. Notice they're all 2 positions away. This bond is 2 positions from this one, and this bond is 2 positions from this one. Normally I wouldn't bother drawing this hidden hydrogen, but I'm drawing the hidden hydrogen right now just so that we can see the correct angle of this equatorial bond. So here's the correct rule for drawing the angle of equatorial bonds, and that's, I think, especially helpful for drawing the equatorial bond in this position and in this position. Please pause the video and try this problem. Now we'll discuss. We can start by numbering the carbons. Now we can look for ionic bonds. Here's a metal-non-metal bond between sodium and oxygen, so we can put in the formal charges for that ionic bond. And that tells us that the O- will act as a nucleophile or a base. Our neutral chlorine is expected to be the leaving group, which makes carbon 1 our alpha carbon. And that would be a tertiary alpha carbon, because carbon 1 is attached to 3 carbon chains, carbon 6, carbon 2, and carbon 7. Now we can choose our mechanism. Tertiary alpha carbon puts us in the bottom row. O- puts us in the right-hand column of the table, so the table predicts E2. Make sure you write down that the mechanism will be an E2 mechanism. So now we know that the O- will act as a strong base rather than as a nucleophile. Following our E2 guidelines, we want to label the alpha and beta carbons. Well, here there are 3 beta carbons. Carbon 6, carbon 7, and carbon 2 are all attached to the alpha carbon. So we have 3 beta carbons to choose from. All of those beta carbons have hydrogens attached. So far they're still candidates for an E2 reaction. Now, in this case, the molecule has already been drawn in a chair cyclohexane ring. So there's no need for us to draw the chair cyclohexane. It's already drawn for us. Now we know that in the chair conformation, the leaving group must be axial. Well, conveniently, notice that this leaving group is already axial. This leaving group is already axial, so this looks like a good conformation for E2. This is the right conformation for E2 because the leaving group is already axial. So which beta hydrogen are we going to use? Well, remember that on a ring, the beta hydrogen has to be trans to the leaving group. And do you see that that eliminates carbon 6? Notice that this hydrogen is cis to the leaving group, which means that it's not a candidate. Notice here that this chlorine is pointing up, and this hydrogen is also pointing up. That means they're both on the same side of the ring, so they're cis to each other. But we've learned that the beta hydrogen must be trans, not cis. So we can eliminate this hydrogen as a candidate. Remember that the reason why it has to be trans is because otherwise it can't be oriented anti to the leaving group. I think it's obvious that this bond and this bond are not oriented anti to each other. This bond is pointing straight up and this bond is pointing partially up, so they're obviously not pointing in opposite directions. So we can go ahead and erase this beta. I can erase that beta symbol because it turns out we're not going to use this beta hydrogen. I think that would be a common mistake on this problem. So to review, we are not going to use this beta hydrogen for E2 because it's cis to our leaving group. But so we used this guideline. For E2 on a ring, the beta hydrogen must be trans, not cis. You can check cis or trans on a chair picture by thinking in terms of up and down. Since the chlorine and the hydrogen are both in the up position, they're cis to each other, not trans. Okay, so that leaves us with 2 more beta hydrogens to choose from. Now, this hydrogen seems like a good candidate because clearly this hydrogen is trans to the leaving group. Our leaving group is pointing straight up, and this hydrogen is pointing straight down, so they are trans to each other. On the other hand, this carbon is outside of the ring. So all of these hydrogens are good candidates. We don't need to worry about these hydrogens being trans to the leaving group because this carbon is not part of the ring. So these hydrogens all seem like good candidates. So how can we choose? How can we choose between using beta carbon 2 and beta carbon 7? Well, now we have to remember that we were asked for the major product, and now this guideline kicks in. Remember that the major product should use the more substituted beta carbon. So let's see which is the more substituted beta carbon. Well, carbon 2 is a tertiary beta carbon. Carbon 2 is tertiary, attached to 3 carbon chains, carbon 3, carbon 1, and carbon 8. On the other hand, carbon 1 is a primary beta carbon, attached to only carbon 1. Well, remember the major product should use the more substituted beta carbon. Carbon 2 is more substituted than carbon 7. Carbon 2 is more substituted than carbon 7. So now I am going to erase the beta label from carbon 7. I can erase this beta label here because we're not actually going to use this beta carbon for our major product. This is the beta carbon that we're going to use. So we used this guideline. The major product for E2 uses the more substituted beta carbon. Now remember, there is an exception to that when you use tert-butyl oxide. Tert-butyl oxide would be an exception, so let's check. Are we using tert-butyl oxide here? No. This base is not tert-butyl oxide. Do you know what the name of this base is? This base is hydroxide. So here we're using a hydroxide base, not a tert-butyl oxide base, so this exception does not kick in. And instead we follow the general rule. The major product for E2 uses the more substituted beta carbon. But make sure you watch out and check whether you're using tert-butyl oxide, because that would be an exception to that rule. Okay, so we've done the work and we've decided that we're going to use this beta hydrogen. Remember, this is a good candidate because it is trans to the leaving group. Remember that the leaving group is in the correct position here because this leaving group is axial, which is what we need for E2. You can clearly see the leaving group and this beta hydrogen are definitely oriented anti to each other. These are definitely oriented anti to each other. Remember, we eliminated this beta hydrogen. This beta hydrogen cannot participate in E2 because it is cis to the leaving group. And we eliminated these beta hydrogens because they would give us the minor product because they're on the less substituted beta carbon. The first time I recorded the explanation for this problem, I forgot a detail. Since I labeled that the O- is acting as the base, I should also have labeled the atom that's going to act as the acid. We determined that carbon 2 is the beta carbon that will give us the major product, and that means that for the major product, we're going to be using carbon 2 as our weak acid that will give up a proton to the base. Now we can draw the mechanism. Here's our mechanism. The base takes the beta hydrogen, pi bond forms between alpha and beta carbons, and the leaving group leaves. Something I forgot to mention. Notice that on this problem, there's no need to draw the other chair flip. There's no need to draw the other chair flip. This chlorine is already in the right position for E2, in the axial position. And notice that we have two methyl groups in equatorial positions, so this should be a pretty stable chair flip. This is a fairly stable chair flip because we're able to get two of the methyl groups in equatorial positions. So we expect this will be a fairly stable chair flip. The leaving group is in the right position for E2 in the axial position. So there's no need, there's no use to drawing the other chair flip for this picture. This arrow tells us to draw a bond between this oxygen and the hydrogen. So now I've shown the oxygen bonded to a second hydrogen. The oxygen started negative. The oxygen started negative and lost electrons, so it becomes neutral. This arrow tells us to break the bond between carbon 2 and this hydrogen. I've done that, and to form a pi bond between carbon 1 and carbon 2. Here's that new pi bond. This arrow tells us to break the bond between carbon 1 and the chlorine. The chlorine started neutral and gained electrons, so it becomes negative. Now, one more issue. Remember that in this picture, carbons 1 and 2 are tetrahedral. But now in this picture, now that they're part of an alkene, carbons 1 and 2 should be trigonal planar. So it's best to change the angle of these bonds a little bit more to show that it's trigonal planar. Now I'll change this bond. So now this bond and this bond are drawn at in a somewhat more accurate way to reflect that this carbon should be in the same plane as carbon 6 and 2, and carbon 8 should be in the same plane as carbons 1 and 3. Maybe that's not perfect, but that's a little bit more accurate way of drawing that these are now trigonal planar carbons. The product that the professor would probably care about on this problem is this one. The purpose of this problem was to give us some more practice with carrying out E2 on a chair picture. This problem was different from the earlier problems because the earlier problems gave you flat pictures and you had to redraw them as a chair. This is a case where we're already given a chair picture. Remember that in this case there was no need to draw the other chair conformation. This was already in a fairly stable conformation with two equatorial methyl groups, and it was already in the correct conformation for E2. The only possible conformation for E2 is when the leaving group is axial. So this was already the correct conformation. We didn't need to draw the other chair flip. The big issue here, remember, was choosing the correct beta hydrogen. We rejected this beta hydrogen because it was cis to the leaving group, using this guideline. We said that the major product here would use this beta hydrogen because this is the more substituted beta hydrogen, using this guideline. The hydrogens on carbon 7 are possible for E2, but they would give us the minor product in this case. Remember when you're using these guidelines that there's a different guideline for ordinary bases or for tert butyl oxide. So it was important to notice that on this problem we were not using tert butyl oxide. That would have changed who the major product was. Remember again, in order for E2 to occur, the leaving group must be axial, because that's the only way the leaving group can point anti to the beta hydrogen. At least that's the case when both the alpha and beta carbons are part of the ring. In this case, the chair picture that was drawn for us already had the leaving group in the correct axial position. Please pause the video and try this problem. Now we'll discuss. We can start by numbering all the carbons. I've numbered all the carbons, including these. No need to look for an ionic bond. This formal charge on the nitrogen has already been drawn in for us. So we can identify the negative nitrogen will play the role either of nucleophile or base. Those are the electron donors. A negative charge makes something want to donate electrons as either a nucleophile or a base. The neutral chlorine will be our leaving group, which means that carbon 1 will be our alpha carbon. Carbon 1 is a secondary alpha carbon attached to two carbon chains, carbon 6 and carbon 2. So we can choose a mechanism. A secondary alpha carbon puts us in the middle row of the table. And now we're using N-. Notice that N- is in the right-hand column of the table. N-, like O-, is both a good nucleophile and a strong base, while the right-hand column and the middle row of the table predicts that the mechanism will be E2. So be sure to write that down. I believe this is the first problem we've worked on where we used an N- rather than using an O-. We can say here now that notice N- is a strong base, so we predict that the nitrogen will act as a strong base. The large majority of the E2 reactions you're likely to see will use O- as the base, but every once in a while you might see the professor use N- as the base. Remember, there's a huge difference between N- and neutral nitrogen. Neutral nitrogen would put us in the middle column. Negative nitrogen puts us in the right-hand column. Also, don't confuse N- with N3-. Notice that N3- would again put us in the middle column of the table. But an ordinary N-, like we have on this problem, puts us in the right-hand column of the table. We want to label our possible beta carbons. We could use carbon 2, perhaps, as the beta carbon. Well, carbon 2 is a beta carbon and carbon 6 is a beta carbon, so we have to choose between them. They're both attached to hydrogens. You can see there's a hydrogen attached to carbon 6, and remember this is capital D for deuterium. Remember that deuterium is an isotope, a type of hydrogen. So carbon 2 does have a kind of hydrogen on it, this deuterium. Both carbon 2 and carbon 6 have a hydrogen or an isotope of hydrogen. So which one are we going to use in the reaction? Well, here we use this guideline. The beta hydrogen must be trans to the leaving group. Notice that this deuterium is cis to the leaving group. This deuterium is cis to the leaving group, which means that it is impossible to use this deuterium for E2. It's impossible to use this deuterium for E2 because it's cis to our leaving group. So I'm going to erase the beta on carbon 2 because now we've determined that we're not going to use carbon 2 as the beta carbon for this E2 reactions. E2 is impossible with this deuterium because it's cis to the leaving group. On the other hand, notice that this hydrogen is trans to the leaving group. The hydrogen is pointing into the page and the leaving group's pointing towards you. So this hydrogen is a good hydrogen for E2 because it's trans to our leaving group. There's no need to use this rule. There's no need to use these rules. We don't need to choose between major and minor products here because there's only one possible beta hydrogen left. This is the only beta carbon and the only beta hydrogen that's possible for E2 here, so this rule is not necessary. So notice that on this problem, it's not necessary to draw the chair conformation. On this problem, it's not necessary to draw the chair conformation. That was really the main reason that I threw this problem into the mix in this video. The main thing that we're learning in this video is how to do E2 problems that involve drawing the chair conformation, but it's important to keep in mind that that's a somewhat unusual situation. Most of the time when you have a ring, you probably don't have to draw the chair conformation. So don't assume that you always need to draw the chair. Now, how can you tell whether you need to draw the chair or not? Well, it does come down somewhat to judgment. Notice that you usually need the chair conformation when there's a large substituent, such as a tert-butyl group. None of the substituents here are especially large. There's no tert-butyl groups. The only substituents are the relatively small methyl groups. That's one clue that we probably don't need to draw the chair conformation in this case. Now, if you want to draw the chair conformation, that's okay. If you wanted to, you could draw the chair conformation here and make sure that you find the chair conformation where the chlorine is axial. If you wanted to, you could draw the chair flip here where the chlorine is axial and use that for the E2, but it's not necessary for this problem. It's okay just to use this flat picture. By the way, I forgot to mention, just to remind you, the reason why the beta hydrogen has to be trans to the leaving group is so that it can be anti to the leaving group. Clearly, this deuterium can't be oriented anti to this chlorine if they're both pointing in the same direction. But it would be possible for this hydrogen to be anti to this chlorine because they're on opposite sides of the ring. To actually show this hydrogen oriented anti to the chlorine, you would have to draw the chair conformation. But again, that's not necessary on this problem. It's good enough to know that we could draw a chair conformation where the hydrogen is anti to the chlorine. It's not necessary to actually do that for this problem. We just know that we could. Okay, so let's go ahead and draw our mechanism. An arrow to show the base taking the beta hydrogen, an arrow to show the pi bond forming between alpha and beta carbons, and an arrow to show the leaving group leaving. Now we can draw the products. This arrow tells us to form a bond between this nitrogen and this hydrogen. The nitrogen started negative and lost electrons, so the nitrogen becomes neutral. This arrow tells us to break the bond between this hydrogen and carbon 6 and to draw a pi bond between carbon 6 and carbon 1. Here's that new pi bond. This arrow tells us to break the bond between carbon 1 and the chlorine. The chlorine started neutral and gained electrons, so it becomes negative. Now we have to fix the geometry here. In this picture, carbon 6 was tetrahedral, but now as an alkene carbon, carbon 6 should be trigonal planar. So we need to change carbon 7 from a wedge to a solid line. Carbon 7 changes to a solid line to show that carbon 6, the new alkene carbon, is now trigonal planar. On the other hand, carbon 2 didn't participate in the reaction, so it stays tetrahedral with a dash and a wedge. This will be the product that the professor probably cares about on this problem. The main purpose of this problem was to remind you that in this video we've learned that there are some cases where you have to draw the chair conformation to analyze E2 for a cyclohexane ring. But the purpose of this problem was to remind you that there's also many cases, even with a cyclohexane ring, where there's no need to draw the chair conformation. Like I said, it's somewhat a matter of judgment when you need the chair conformation, but you're more likely to need the chair conformation when there's a large group like a tert-butyl group. And like I said, if you're not sure, it doesn't hurt to draw the chair conformation, but it might lead to confusion and take more time than you need to. So this is a problem that we could solve without drawing the chair conformation. We also reviewed the idea here that on a ring, the beta hydrogen must be trans to the leaving group. That's how we knew we were going to use this hydrogen for E2 rather than using this deuterium for E2. And also, I think this is the first problem we've worked on where we used an N- as our strong base rather than an O-. Please pause the video and try this problem. Now let's discuss our solution together. We can start by numbering the carbons. This is the solvent and won't participate in the reaction, so I won't bother numbering those carbons. Now the ionic bond and formal charges were already drawn in for us, so we should just notice that we have a negative sulfur here. So we expect that the sulfur will be a nucleophile or a base. Remember that a negative charge makes you want to donate electrons, and the electron donating roles are nucleophile and base. We see a neutral chlorine, which looks like a good leaving group, and that would make carbon 1 into our alpha carbon. And we can notice that carbon 1 is a secondary alpha carbon. So we're ready to choose our mechanism. A secondary alpha carbon puts us in the middle row of the table. And we're using S-. We find S- in the middle column. The middle column of the table. S- is a good nucleophile, but a weak base. So if we find ourselves in the middle column of the table and the second row, the table predicts that the mechanism will be SN2. Write down the name of that mechanism. So the main purpose of this problem is just to check whether you're awake. Again, we're mainly focusing on E2 mechanisms in this video series, but you can't assume the mechanism is E2. You have to use the table. Notice that there's a huge difference between an S- and an O- or an N-. Even though sulfur is in the same column of the periodic table as oxygen, it has somewhat different reactivity. If we were using an O- for this problem, we would expect an E2. But notice that with S-, we're not generally going to expect E2 to be the major product. With an S-, we generally do not expect E2 to be the major product. Instead, the major product here is SN2. So make sure you always use the table to determine the mechanism. Remember that you can only do that if you have the table memorized. So no time like the present. If you haven't done so yet, make sure that you memorize this table. Well, now we've decided that we're going to use, well, we're doing an SN2 reaction. And remember that for an SN2 reaction, we use a nucleophile, not a base. So now we're expecting the S- to act like a nucleophile, not a base, and we can draw our mechanism. I guess I'll say here that carbon 1, since it's attached to the chlorine, carbon 1 has a delta positive charge, and that's the clue that carbon 1 is a reasonable electrophile. So now I've labeled all the roles that are going to participate in that SN2 reaction. You should have memorized that SN2 consists of a single step. In that single step, the nucleophile is going to join the alpha carbon. And simultaneously, the leaving group will leave the alpha carbon. So here are the arrows to show that. Now we can draw our product. This arrow tells us to form a bond between the sulfur and carbon 1. I formed a bond between the sulfur and carbon 1. The sulfur should still be bonded to its hydrogen. The sulfur has a covalent bond to the hydrogen. There's no arrow telling us to break the covalent bond to the hydrogen, so the sulfur is still attached to the hydrogen. The sulfur started negative and lost electrons, so the sulfur becomes neutral. This arrow tells us to break the bond between carbon 1 and the chlorine. The chlorine started neutral and gained electrons, so the chlorine ends up with a negative formal charge. And also, we want to get the stereochemistry here correct. Remember, you should have memorized that an SN2 reaction results in inversion of stereochemistry. So whereas this chlorine was on a wedge, this sulfur comes in on a dash. In the SN2 series, we discussed this rule. Whenever a nucleophile attacks an atom that's attached to a leaving group, the nucleophile always attacks from the side opposite to the leaving group. So here the sulfur is attacking carbon 1 while it's still attached to the leaving group. Since the leaving group is in front of the page, the sulfur has to attack from the opposite side from behind the page. So the sulfur ends up on a dash. This is the reason that we expect an SN2 reaction to give us inversion of stereochemistry. The stereochemistry matters at carbon 1 because there are cis-trans relationships around the ring. And the original ring had a cis relationship between the substituents, and after the inversion of stereochemistry, the product has a trans relationship between the substituents. So the stereochemistry does matter at carbon 1 because it matters whether this substituent is cis or trans to carbon 7. Those would be two different products. Here's the product the professor probably cares about on this problem. Okay, so the main purpose of this problem was to make sure that you're using the table to determine the mechanism. We've mainly worked in these videos with O- and once with N-. Notice that other negative charges behave quite differently. S-, Cl-, Br-, I-, all of these negative species here behave much differently than O-. These negative species don't give us E2 reactions. So make sure you pay attention to the exact species that you're using as your nucleophile or your base, so you know what the correct column of the table is to use. And this also gave us a chance to review SN2 reactions. I hope that you're well familiar with the idea that an SN2 reaction gives you inversion of configuration at the alpha carbon because of this rule. Remember, you can review SN2 in more detail in my series on SN2 reactions. By the way, this molecule, again, played the role of a solvent, and it didn't participate in this reaction. This solvent is acetone. In the SN2 series, we learned about the solvents that are commonly used for E2, SN2, SN1, and E1 reactions. And we learned that acetone is a common solvent. Acetone is a solvent that does not participate in SN2, SN1, E2, or E1 reactions. So it helps if you're familiar with these common solvents. I discussed those in the SN2 series. That would help us to see that this solvent on this problem will not participate in the reaction. Please pause the video and try this problem. I hope that you actually did write out the complete table from memory on paper. Here's the answer. Check what you wrote down to make sure it matches this table. And I hope when you wrote down the table, I hope that you included the identity of the species in each column. You can't use the table unless you know which of these species go with each column. So you need to have memorized, for example, that neutral oxygen is in the left-hand column, negative oxygen and negative nitrogen are in the right-hand column, and this miscellaneous collection of species go in the middle column. So make sure that's part of what you have memorized. If you made any mistakes, I encourage you to take a blank piece of paper and write out the table again from memory. Just keep writing out this table over and over from memory until you can easily write it 100% correctly. And that's something that you probably need to do every day between now and the midterm. It's crucial for your success on your midterm that you have complete mastery of this table. So you want to keep practicing writing out this table from memory every day until the midterm. When you take your midterm, it might be a good idea to start by writing down the table on some scratch paper so that you can refer to it during the test, but that will only be effective if you have that table well memorized. In the next video, we will proceed to discuss our next E2 related topic. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge at my Patreon page. You can visit my Patreon page by clicking the link on the screen, or by using the link in the video description box. Thank you.